Yes, good afternoon. I would like first to inform you about a bit about the mini research that we should do, and that is mini research number 1. So I will be distributing you these mini researches because Mr. Andres cannot be today, so I will just use this as a sample. So every research is different, and there are some references added. In some cases, references are in the foreign language, which is not a problem for you because you know how to use dictionary, etc., etc. Now, so this foreign language is in one case, in several cases German, and in one case Russian. So, for example, Mr. Andres has this title of this work is Some Problems Involving Bessel Functions. Assignment is check the derivations and numerics on a computer of the paper by Engelhardt. And this article by Engelhardt is Die Einheitliche, etc., etc., 1954 in the journal The Stahlbau. Now, deadline is November 13, 2003, by which time, actually, before this November 13, you will get the second assignment. Now, there is small differentiation. The undergraduate students got, say, half an order of magnitude less work. Not that this is much work in also for graduate students, but just at least I tried to, at least in the initial condition, it seems to me that it is 5 times easier, so approximately half order of magnitude, not 10 times, but 5 times. So I will give now this to you, and you may have a look at your works. If you have any question. Yeah, actually, in one case, foreign language is Japanese. But equations, differential equations, naturally, we do not need, in that case, to know the foreign language. We need just to see the equations. Now, about some very small comment about homework assignment. Just very small homework. Now, the homework usually is as follows. What is actually the homework? Homework is so there is a student. Student gets assignments. Okay, then he hands it to the lecturer. Then lecturer checks. And this goes back to the student. So this is some feedback mechanism, is it right? But you may want to make this figure, which is very simple, much easier than Bessel function. Now, sometimes you do not have to hand the homework to the lecturer. What does it mean you do not have to hand? For example, if you get, for example, P critical equals, for example, pi square EI, over L in 7th power. So probably such a homework you don't have to hand because, I mean, the dimension is not good. Or if you have, for example, some expression involves 1 plus 5/7 L. Okay? That means like something non-dimensional, and this has a length dimension. So we already know that that is a mistake, so person do not have to hand to the lecturer such a work. He can actually, or he or she can actually check this and immediately find the mistake. So what we are saying that please, before handing, check yourself. Does it make sense? Okay, if you think it is nonsensical, so naturally you don't have to give it to someone else. Okay? Now, that is one announcement. Second one will be as follows. Yes. Now we would I would like to tell you that we are actually dealing more or less simultaneously with three topics, and that is Lyapunov methods. That is one thing. Second is theory of plates. And third, if you recall, it was Bessel functions and their applications. So many, actually, several of you got assignment on Bessel functions and their applications. So you already know what Bessel functions are. Actually, from the McLachlan's book, you actually got pages by Mr. Andres, so that we know what are the Bessel functions. So this knowledge will be extremely useful in getting the solutions. There is also one book whose title I don't remember. Can you imagine? I remember just the author. Either it says Bessel functions or something else. But the main thing is that it contains something that is called Lomel functions. Now, Lomel functions are Lomel functions satisfy non-homogeneous Bessel functions. Non-homogeneous Bessel functions. What is non-homogeneous means right-hand side is not 0, but it equals z in some power, if we had mu, then say in power nu. Okay, that is the right-hand side. So that means that polynomial right-hand side. Okay. So those who have papers in German and in Russian, okay, so those people will need actually to see also the Luke's book, as well as closely read McLaughlin's contribution. Now, we dealt actually, if you remember, we dealt with chapter number 7, which dealt with instability problems governed by differential equations with variable coefficients. We already started with that. Paying attention that Bessel function naturally is an ordinary differential equation with variable coefficients. So in chapter 7, we will need Bessel functions. It is extremely advisable, naturally, when you come to bring a folder in which you have entire lecture notes, so that if and when I'm using the lecture notes, then maybe you can write on the margins or inside the manuscript, etc., etc. Now, so we dealt, if you remember, with two cases that I'm not going to repeat. First, I brought extremely simple cases, and this first case was due to Russian scientist Zhanitsin, 1955. So he considered such a moment of inertia, that means parabolic variation of moment of inertia, and he was able to obtain closed form solution that equals 8 times EI0 divided by L square. Then we talked about an Englishman, Duncan, who considered moment of inertia also as a parabola, but a different one, not necessarily a symmetric one, like as was considered by Zhanitsin. So that is 1937, actually. This predates Zhanitsin's contribution, but I think Zhanitsin does not quote Duncan. He did not know Duncan's work. Now, Duncan also guessed very beautifully. You know, it's an unbelievable guess, very talented guess of the solution of this equation. Can you imagine? So he's found that this polynomial is a solution, and he found also the buckling load, 60 divided by 7 EI0 divided by L square. Now, generally, we don't have such closed form solutions. However, there are something that is exact solutions, means that we can still find something that is exact, but does not look so intriguingly simple as Zhanitsin and Duncan gave. And we will deal actually with bucklings of the clamped free column under its own weight. If you remember, we actually started our discussion in the very first lecture with such a topic, that monuments, so to say, are this case. For example, look, this is a Washington monument, okay? And there was this light show when they finished the restoration of it. And because that is a long monument, okay, this is from newspaper in 1998, so it says monumental effort. So that is how its various parts look like. And now, biggest monuments are not in Americas. So this one is from Shanghai, and but not the biggest one also. That is 95 stories, 1,509 feet tall. Okay, that is in Shanghai. Then there are two towers, actually, in Malaysia. Kuala Lumpur. That were the longest towers up to past week actually. But past week, no, I'm actually misinforming you. This week, probably they knew that I have a lecture on this topic, and therefore they just made the construction faster. So there is this new building that is Taipei 101. That is called Taipei 101, and I actually cut from the newspaper the picture of it, but as a true professor, I don't remember where I put it. So now I would like you to get from some website. I'm sure that websites have both Kuala Lumpur and Taipei towers. And please bring that picture here. Next week, actually, we will have a next week, yes, today is Thursday. Next week, we will have a presentation by Mr. Berezhnoi, so he can bring, or maybe you can bring him this picture, so he will present the picture of Taipei 101. Now, naturally, that these buildings are susceptible to the buckling, okay? Now the question is how to do the analysis. An analysis, you would be very surprised, was actually started by Leonhard Euler himself. So not only he gave this surprising solution for the clamped free beam under the concentrated load, but also considered various topics that were, so to say, at that time, naturally not of mathematical interest. Now, so what we are considering is actually a column that is under its own weight. So load, so that is this Q. Okay? So in our differential equations, we do not have distributed, that is a distributed axial load. You see, probably not much was going in St. Petersburg. Leonhard Euler, when he graduated in Basel, there was no job availability in Switzerland. However, he had very good friends. One of his teachers just got a job in Russia. So that friend, Bernoulli, you remember probably his name, invited him to Russia. So he went there. So he was a court mathematician in Russia. Most unfortunately, he was not very accepted as a human in the court, because usually during the dances, etc., they don't discuss mathematics, they discuss something else, like politics, maybe religion, maybe something else, maybe some people. So Euler was a very straightforward person. So he was not very much liked in the emperor's court. And there was probably not much going in St. Petersburg in those days in comparison maybe with other courts of Europe. So he was imagining various problems and was solving them, Leonhard Euler. But at some time he got fed up with the Russian court. He actually wrote to some friend that if you are talking in this country, they are hanging you. That he wrote in 1747 approximately, many years ago. So he decided that he is leaving Russia and went to Germany, where he spent considerable amount of time. However, in German court, he was also not accepted because he did not like to get involved in politics, so to say, and gossip and slander, etc., etc. So Frenchman, very famous Frenchman, Voltaire, actually laughed at him at any occasion. I mean, they knew that his response would be very straightforward, therefore planted various remarks for him. to which he would respond straightforwardly, and emperor did not like him either. At that time, Russia got a new emperor, and Catherine wrote him that they are going to, if he comes back, he's going to get any salary that he wants. He just has to number the figure. So he was a shy person. He did not give any, did not suggest any money. So the emperors took the previous salary and added 10 at the end and invited him back. So he got a contract. So Euler sits in Berlin, got a contract, and he is requested to write in this contract actually what he is going to do for so much money. So Euler wrote that I, Leonhard Euler, oblige myself to write so many papers that the printers of St. Petersburg Academy of Sciences will need 40 years after I, Leonhard Euler, die to print everything that I will write. So it is very easy, of course, to write such a thing, because if you did not fulfill the contract, so then one cannot take money back because person will be dead already for 40 years. But interestingly, so 40 years. However, it took to that printer 45 years to print all the papers by Euler, all the papers. And interestingly, maybe I sent it, in 1901, they did start to reprint all his works. And already there is, I think, 70 volumes, each of them 500 pages. So it took already more than 100 years to find everything, etc. But they did not finish yet to reprint all the works by Leonhard Euler. So we are dealing with his analysis here, and this differential equation looks like this. So without Leonhard Euler, actually, we as modern people would not have this modern life, because, say, just if we talk about buckling, it is used in air. There will be no flights without knowledge of column buckling, or there will be no usage of cars or ships, etc. Probably we would never meet each other because we would be staying in the countries where we were born, because there will be no means of transportation. Okay? But because of Leonhard Euler, we met each other and we would like to learn what he had to say. Now, this is, of course, Q then. Okay? So we are cutting here at some distance of x. Okay? Then n of x is negative, of course, because at this location, the okay, let us see this part. That is a free body diagram. So this is n of x. N of x is compressive. Okay, if I will take this element, small element, this small element will be under compression. Yeah, interestingly, that the emperor's court was very friendly second time when he came back, that his house was burned during one of the disasters, but the emperor again asked how much would it cost to rebuild the house. And when treasurer gave the price, emperor again added 10 at the end. And he was paid 10 times more than that burned house. I think that emperor knew that scientists should be treated very well. Do you agree with me? Okay, thank you. Okay, not that we wish anyone's house to get burned, but now, n is negative. Now, how much is n? It's written here. N is minus q, L minus x. Because this is x, and this one is L minus x. So L minus x times q equals n of x. And it is negative, minus q L minus x. Is something wrong?
Sorry, I had to change up your battery here.
Oh, okay. Actually, it's your battery because I did not bring it.
There you go, thank you.
Thank you very much. My battery does not need change. Their batteries need a change. Okay. Let us continue. Now we have this is negative, but n of x is with negative sign. So here is minus n of x. So we get plus d dx. So differential equation itself, if you recall, is EI w forced derivative, then minus n of x w prime, and then derivative equals 0, yes? So we substitute n of x, multiply by first derivative, and then we take again first derivative. So then that is an equation. EI, forced derivative of w with respect to x, plus first derivative with respect to x, ql minus x dw dx equals 0. Now, because what is this? That is an ordinary differential equation with variable coefficients. Because that is a derivative, fourth order, and here we have d dx, so we can integrate once and get a constant here. So that is EI, third derivative of w with respect to x, plus ql minus x dw dx equals a. A is an integration constant. Now, boundary conditions are at the clamped end, w equals 0, dw dx equals 0. X equals, when x equals 0. Now, at the end, moment equals 0, and then effective, if you remember, effective shear force equals 0. Now, effective shear force then equals, oh, I should increase actually. EI is the third moment, bending moment, of course, on the top equals 0, because there is nothing that, there is no moment applied there. And here that is a shearing force, and shearing force equals EI d3w dx cubed, and then there is this term that should be evaluated at x equals L, but x equals L, this term vanishes. So just the shear force. So effective shear force equals the shear force. Okay? Now, let us write, this differential equation is right, no, this differential, of course, this differential equation is correct for any x. Naturally, it is also correct for x equals L. So let us substitute here x equals L. When x equals L, this term vanishes. But at x equals L, we just showed that this third derivative equals 0. So this is 0, therefore a must be 0. Once we substitute x equals L, we find that a must be 0. So therefore, we get this equation. EI d3w dx cubed plus ql minus x dw dx equals 0. So we got a third order differential equation, and we satisfied one boundary condition already. Which boundary condition we satisfied? That the shearing force equals 0 at L. Okay, because if I substitute here L, naturally this equals 0. Now we have to do the analysis, and I would like checking pages 7, 8, 7, 9, 7, 10, 7, 11, 7, 12, and 7, 13 is your homework. So you may want to write it down. Check pages 7, 8 to 7, 13. And now we would like to make a substitution. Now what we are doing actually is as follows. We are trying to reduce this differential equation to the Bessel equation. Okay, you may ask, how do you know it's reducible to the Bessel equation? Of course, this should be asked to the first person, why that is reducible to the Bessel equation. But now we are just doing substitutions, and let us see that this equation will be reduced to the Bessel equation. By the way, Bessel equation naturally is not an easy task, even if I am getting Bessel equation. If I am reducing, still solution of the Bessel equation will be given in infinite series. Is it right? So, however, at least we know that Bessel functions have been extremely well studied. There are, you may want to write down that there are tables of Bessel functions, there are procedures, etc. By the way, sine function is also evaluated as an infinite series. Cosine function is also evaluated as an infinite series. So this solution is not less good than having a solution in trigonometric terms, which are also infinite series. Now we introduce a new variable, which is 2/3 square root from q divided by ei, L minus x cubed. Now, let us look at the first derivative of z. Okay, so that is a new variable. Please write down that it's a new variable. New variable. Now, dz dx we would like to calculate. So first of all, we have, when I evaluate with respect to x, naturally I will have to take derivative from this expression L minus x. So in front of x I have minus sign, so there will be minus. Then I have q over ei square root here, so that is the coefficient that is repeating itself. Now we have, look please, we have L minus x in power 3/2, is it right? That is 3, and that is a square root, so that's 3/2. When I differentiate it, I will get 3/2. But 3/2 will be multiplied by 2/3, I will get 1. So there is no coefficient here. That is why this 2/3 is written, because we know that 3/2 will be coming out. Okay, that is why this 2/3. So that is 3/2 and minus 1. Okay, because when I differentiate, so I'm getting then 3/2 minus 1, it is just 1/2, so this is this one, 1/2. So please take out this parenthesis. This parenthesis on the right-hand side is superfluous. So that is a derivative, dz dx. Now from this equation we can also find L minus x. Okay, what is L minus x? So we can take first of all everything squared, so we will get z squared. Now let us do this by hand. Let me write it down. Z equals 2/3 square root q over L, and then L minus x 3/2. Okay? So I can write down L minus x 3/2 from here equals 3/2 times z I wrote L here. That is not correct. That is EI. Okay, here there was a mistake. I should have EI. I wrote L somehow. I don't know why. Okay, so we have L minus x cubed. That is 3/2 times z times EI over Q. So now we take everything in the power 2/3. So then we will get L minus x. So power, I will write down power 2/3. So we will have 3/2 z in power 2/3, and then EI over Q is in power 1/2, and it is in power 2/3. So 2/3, 2 and 2 are gone, will be 1/3. So that is this. So we get this expression that we have here. L minus x equals 3/2 z in power 2/3 multiplied by EI over Q 1/3. Okay? Now we want to calculate this dz dx. So we already had this dz dx. dz dx equals minus q over EI 1/2 L minus x 1/2. That is, that is this equation, previous one. That was dz dx. Now I will substitute this L minus x, we wrote, equals 3/2 z in power 2/3 EI over Q 1/3. So I want this to be substituted here. Okay, L minus x 1/2. So we get dz dx equals minus q over EI 1/2. Now L minus x in power 1/2. So that is 3/2 z 2/3, and that is in power 1/2. Then we have EI over Q 1/3, and in power 1/2. Okay, so this gives us dz dx equals minus 3/2 z 2/3 power 1, 2 is 1/3. Now will be q in power EI 1/2. Now this is power 1/6, but that is power q over EI in power minus 1/6. Yes, because that is the opposite. So therefore, this will be a 1/3 power. So this power is 1/3. So, and here is also 1/3. So everything boils down to 1/3. dz dx equals minus 3/2 z q over ei in power 1/3. Okay? Or I can just show you this expression. So we derived this expression. Okay, dz dx equals minus 3/2 qz over ei 1/3. Now, why did we need this? Because we introduced new variable z. So I would like to write dw dx that is in the differential equation as a function of z. Because now instead of x, I have z. But dw dx I have. So I would like now to calculate dw dx, how it looks in the new coordinate system. So I'm writing dw dx equals dw dz, dz dx. Okay? So, but dz dx we just evaluated. That was here. That was this dz dx. So therefore, I'm getting minus 3/2 qzi 1/3 dw dz. Okay? So we evaluated the first derivative of w. Look, please. W now is a function of z, and the first derivative with respect to x should be rewritten in this form. And it depends upon z. Now we would like to evaluate additional derivative, d2w dx square. So one thing is immediately clear, that every time that I differentiate with respect to x, I'm getting this coefficient in front of dw dz. So if I'm differentiating again I will get minus 3/2, etc. So minus times minus will be plus 3/2 q. Forget now z for a moment. Q over ei 2/3, not 1/3 but 2/3. And now I have to differentiate. So that is d dz, is it right? Here it says, look, dw dx, whatever function is there, I have to evaluate dw dz, is it right? And now the function which we have is z in power 1/3 times dw dz. That function should be differentiated with respect to z. Now I'm differentiating. So I will differentiate first z, this one. Z in power 1/3, we got 1/3. Okay? Then we get dw dz plus, now we have what is there, d2w dz square. You don't see this. Then we have the third derivative. Let us see what Timoshenko and Gier have to say. Please derive this equation first. I have to find this. $100. Now, interestingly, this can be found, this problem is described in the book by Timoshenko and Gier. I would like you to get this book from the library. Timoshenko and Gier, Theory of Elastic Stability. Who has this book? Did anyone check out? Say it again?
I think I did.
Okay. Is that an only book?
Yeah, I think it was on.
Yeah, if it is an only book, maybe you can copy, maybe you can come to me and
It's not a virgin, it's probably another one.
say it again.
It's not a virgin, it's another one. It sounds an old book. It's really old.
It is an old book. My book is also old. I just kept it nicely. It's, since 1961. This book is since 1961. Okay, so interestingly, but I cannot check this really. I did not check this event, but I would like you to check maybe. Look what Timoshenko says about this problem. This problem was discussed first by Euler, he says. Okay. This problem was discussed first by Euler, but he did not succeed in obtaining a satisfactory solution. I don't remember this. I somehow thought that this problem was solved by Euler correctly. C. Todhunter and Pearson. Maybe we will ask to get this from Miss Santoro, because she already got this book once, so she at least knows where this book is located physically in the library. Maybe she just enters and without checking the call number just knows where exactly the book is located. Now, History of Theory of Elasticity. And volume 1, page 3950. Please check whether or not on page 3950 it is indeed written. That book is even older, 1886, Mr. Plasencia. That book is older than anyone, I suspect, in this room, any of the students at least. Okay. Now, this problem was solved by Greenhill. I think I have his paper. Proceedings of Cambridge Philosophical Society, Volume 4 in 1881. Okay? Etc., etc. There are several, at least one problem which Euler did not solve correctly, but I personally am telling you that I did not recall that this problem was not solved by him correctly. Now, then we calculate the third derivative with respect to x. And what we get, please check, that is you have to check. What we get actually is this equation. Look, please. d3w dz cubed plus 1 over z d2w dz squared plus 1 minus 1 over 9z squared dw dz equals 0. That is an equation that is obtained. Now, it makes sense because there is this dw dz to denote dw dz as some new function u of z. Then this thing is second derivative of u. And I also multiply everything by z squared. So I will get then in front of this z squared. So this is second derivative of u. Then z squared, so we'll get z du dz. Then here is z squared minus 1/9 u equals 0. Okay, so this is a Bessel equation. And so at this moment, maybe it makes sense to just stop for a second and see what is the general direction this course is taking us. This course will discuss three things, three seemingly opposite things. One, we already discussed closed form solution. But this is rare. Okay, very rare actually. Very rare to have closed form solutions. To remember, Zhanitsin and Duncan had to guess solutions. I succeeded not to guess, to develop some polynomial method of solving problem, but it is extremely rare. We are just very happy, I would say. I'm actually personally also grateful also to Euler himself, because he did not solve that problem with polynomials, so he left it to us. Otherwise, I'm very, very surprised that he did not solve it, because that was just a, he could have gotten it, just in 5 minutes, so to say. So, closed form solution. It was decided for above to leave that solution for us. Now, then there is exact solutions. That is what we do now. Exact means Bessel, etc. Bessel functions, trigonometric functions. So that is also rare. This is extremely rare. That is like winning lottery. Okay? This is like winning 3 numbers in the lottery. If we are using, so to say, lottery. And then we will be dealing with approximate solutions. Approximate solutions. So approximate solutions are already for any problem. Okay? So actually, if we talk about solutions, so then, so these are the solutions. Everything here is a solutions, okay? Points here is a solutions, okay? This looks like an apple, I think. This reminds me of saying that an apple a day keeps doctors away, okay? So this is solutions, and it keeps our problems away. Now, solutions are of 3 kinds. There is subset of exact solutions. Then there is a small subset of closed form. I did not want to leave CF, otherwise you may think later that it's clamped free. So it's not only clamped free, it is closed form. And the rest is approximate. So, percentage-wise, if we talk percentage-wise, if you want, so probably 99.9% of the problems, or maybe more nines, is approximate solution. Then maybe 0.1%, 0.09% of the problems is exact solutions. And then maybe 10 times or maybe 100 times less than that. So 1% of 1% of the problems, so maybe even less, is closed form solutions. Okay? So availability is like that, okay? So if this is, say, platinum, if we talk about precious stones, so this is gold, so then this is an iron. Availability. So there is lots of approximate solutions are, everyone should be able to find approximate solution once you get a diploma. It does not mean that before getting diploma, you don't have to get the approximate solution. But approximate solution is for everyone. Exact solution is a gold, and this is the jewel. Okay, by the way, it is not only because it is so rare, these solutions, because when I have approximate method, I don't know whether this approximate method, how good it is. Okay, I have no idea whether my method that we are having numerical solution is good or not. So at that case, we can check whether that method, let us solve this problem that has exact solution. If my approximate method gives the same solution that here, then at least I could sleep better. I don't mean during the work, I meant later. Okay. So look, please, it's very good news that this method is giving us Bessel equation. Now, what is a Bessel equation itself? Like Mr. Berezhnoy and Mr. Andres told us past time, if we have z squared d2u dz squared plus z du dz plus z squared minus n squared u equals 0, then that is a Bessel equation, and n is an index of the Bessel function, this n that appears here. Okay, it is so denoted. And you remember that Bessel function is called Bessel because he was not the first one who suggested that function. You remember that? That was suggested by Bernoulli, who was a teacher of Euler. Bernoulli is also a very famous name. Naturally, Bernoullis they had the entire dynasty of Bernoullis. Okay, so that it started from one grandfather to the grandfather's to grandchild, and this grandchild's grandchild, and his grandchild. So this family occupied more than 120 years. There was not 1 year in French Academy of Sciences that there was no Bernoulli sitting there. Okay, and French Academy of Sciences was the most well-known academy of sciences in the entire world. So 120 years, Bernoullis occupied the place in that Academy of Sciences. That means that it was not given from father to son. A person should be elected to the membership. Okay, so the solution of that Bessel equation is some constant C1 j sub n, where n is an index, of z plus C2 j in power minus nz. Where Jn is called Bessel function of the first kind, of order n. And we know, how, we already got this infinite series. Bessel function of nth order equals this expression. And this expression can be evaluated either numerically on the computer. Naturally, you are not writing in the computer like sum up from j equals 0 to infinity. Is it right? You cannot give such a command because computer will not understand that. What does it mean to infinity? You are just summing up to the point. You will write here capital N, some n, big N, or M, or you denote according to, say, your last name's first initial, for example. You can denote that. And then you are saying, I will calculate, say, first 100 terms. Then I will add the 101st term. If 101st term has a contribution that is, say, 10 in minus 5 times what was already with 100 terms, then I will say, okay, I don't want such a precision. I don't want, additional term. I will finish the calculation here. So you are adding this series until when it is really you don't feel anything there. Okay? That is like, when very good dessert is served, you want to clean the plate so that almost nothing is left. Okay, you are finishing when almost nothing is left. Okay, you see point here, point there, but already your fork cannot take it, so to say. in, in, in this particular case, we do not say that 4 cannot take it. Computer can, of course, calculate and calculate. But we are saying that we are just satisfied with that. It's okay. And we can finish the calculation of that. Now, gamma function is a function that is denoted by this series, by this integral. And this, first of all, there are tables of gamma functions. But even more importantly, computers have the special function in the special function library, gamma functions. Many computers have also Bessel functions. So you should find special function library. Because people do not usually invent wheels, or we do not write programs for writing the Bessel functions. In a Bessel function, as we know, he wrote this article in 1824, but Euler wrote, but Bernoulli wrote the article in 1781. So it's already a long time that mankind or humankind is dealing with this problem. So there are programs available. Now, Bessel functions have some nice properties, that derivatives are proportional to the functions. Let me see if Luke, I have a reference for Luke at the end. Yes. Okay, that is at the end, actually, we do have. Please get this book if it is available in library, and if it is not available in the library, you can order it by interlibrary loan. Luke, YL, integrals of Bessel. Integrals of Bessel functions. And maybe someone, let us ask this Miss Gentilini, because Miss Santoro already is ordering something. So Lommel, we can ask her to order, but I don't know whether she will succeed. That is a German newspaper, Mathematische Annalen. So Mathematical Communications. Volume 9, pages 415, 444, 1876. So Lommel introduced there his functions. His function. And that function is used by Luke, and we are going to use later, not today. Now, I would like to show you from my lecture notes one of the pages. As you see, you may see whether you need glasses or not, that there is very big mess here. Is it right? You see lines, I have crossed, I have redone things, etc. Because you will have a lot of time at home, I would like you to make correct derivation here. At least you know what I'm doing on the left-hand side, and then do the correct derivations. So it is a homework. Pay attention that this homework is not person-specific. That means that I do not give you, like this is not like a mini research that is person-specific. That means everyone got a different research. That is a common homework. That means that I naturally welcome, not only I am accepting, but I even welcoming your cooperation between each other. So that when you sit together, first of all, it takes less time, and second of all, the result is better usually because you can already criticize each other. Like if dimension is not correct, you will say, come on, that is, you cannot add, kilograms to meters. We don't know what we are going to get, etc. Now, we do have next time a lecturer who is Mr. Berezhnoi. He will start his discussion with Bessel functions and the second function. And we did have two students who already starred in our presentations here. These are Ms. Gentilini and Ms. Santoro. And Mr. Andres already also starred here. And Mr. Berezhnoi will be starring. Who else? Who wants to volunteer from remaining 3 students to give this derivation next time. Who wants to volunteer out of the... Okay, Mr. Plasencia will volunteer to make derivation. Then maybe you will also check together with Ms. Santoro Euler solution. Do you remember? Because it was said that Euler did not succeed, so please provide us with some historical data. What has happened there? And now the main thing is, I will go to the end actually. It turns out that we are left to remember, like, yes, past time, Mr. Andres considered vibrations of the heavy chain. And that was reproduced from the, or heavy string. That was reproduced from the book by McLachlan. That was vibrations. There, he ended up with one Bessel function only. The second Bessel function was discarded because it would go to infinity at 0. So here too we are ending with Bessel function of minus 1/3. So we are getting that u of z equals C2 Bessel function of minus 3 of z. So here z, now at x equals 0, displacement should vanish. And now what is displacement? This u, if you remember, was a derivative of w with respect to z. Is it right? U is dw dz. So in order to find w, we have to integrate. So because we have to integrate, therefore we get w equals integral of this expression, plus therefore there is some constant here. So we get actually, look please, from here, see, we get that integral of Bessel function, and here is 1 in front of d. Second equation does not have d, so in front of d is 0. And that is j minus 1/3 power. So this, we are very happy here because this integral should not be evaluated because it's multiplied by 0 anyways. Because you see, if you are not watching this movie to the end, you may get disappointed because you may say, come on, nothing good happens in this movie, I'm stopping. Indeed, here, when we get an integral, there is a place to be disappointed. Come on, we worked so hard, we got integral from Bessel function. How in the world we can deal with this? But it's okay. We continue to watch, and we see that at the end, the hero that we want to win is winning, because this is multiplied by 0. What is left is Bessel function of minus 1/3. Z 0 equals 0. Now, that is why I asked you, Mr. Andres, to talk about roots of Bessel functions. It turns out that root of this function is 1.866. So, and we will continue the next time. And before that, you will be all specialists in checking this part. Thank you very much.